Hello, everyone. I decided to do two more recordings. So two more MP4 files will be uploaded on Canvas later today. It's the 9th of November. And I decided to do these two extra recordings in order for me to help you better prepare for the exams. Now, if you just Google past exam papers at Newcastle University, you are going to come to this website. Okay, so if you come now here and you type EEE8153, which is the code for our module, and you click search, unfortunately you will not find anything with this code. Now, so what you have to do is to come here and type 8013, because in the past the code for this module was 8013. So if you just click on this now, what you will find here is 3 exam papers. Now, I'm going to start with this one. And there are a few things that I would like to explain. First of all, it is 2 hours and you have 3 questions, while the exam paper that you will have will be 3 hours and 4 questions. The reason for that, also, if you check this exam paper, you will not find any questions on MATLAB. This is happening because back in 2018, 2019, there were 2 exams for this module. One was like this, like a closed book exam, where we were asking the typical questions about state space and so on. And the second exam the second exam paper was another 3 hours. So your fellow students, they had another exam of plus 3 hours, only using MATLAB. So they were going into the computing lab and they were answering MATLAB-based questions. If you want, I can send you that past exam paper. The problem was, though, that the students, they found that 2 plus 3 hours, 5 hours was probably too much for a module, and they have asked me if I would be kind enough to reduce the assessment. So for that reason, after 2019, so 2019, 2020, the exams, they were made, the 2 exam components, they were merged into one assessment, one exam, which was 3 hours and 4 questions. And we're going to see this on the second day of recording. So for this first recording, which is about the paper 8013, 2018, I'm just writing on the visualizer the year of the exam paper. So let's try now to understand this paper a little bit better. First of all, it is asking from us to solve a second order ODE. So I'm giving the ODE, the initial conditions, solutions, map this into a state space, solve this using the eigenvalues and the eigenvectors, solve this using the state transition matrix, and comment on the results. So this is what I'm going to do now, step by step, so that you will be able to understand the type and the difficulty of the questions that you will be asked. So let's see now how to share my visualizer. Excellent. So the ODE is x2 dots plus 2x dot plus x equals 0, and the initial conditions are 1 and 0. Okay, now from this ODE, I can immediately go to the characteristic equation. Now, for those of you that you are good with maths, you can immediately see that this is going to be a classical identity, r plus 1 squared equals 0, and hence r1 equals r2 equals r equals minus 1. If you don't see this immediately, just use the classical formula with the discriminant. It is going to give you the same result. So I have found now my eigenvalue. So my first solution will be e to the minus t. And we have also seen that in ODEs, the second solution will be t e to the minus t. Sorry, I forgot, of course, to mention here that this is a stable system. So these are now my two ODEs. And because of that, I know that later I'm going to need the first time derivative. It's going to be e to the minus t. And this is going to be e to the minus t. Please remember, this is a product of two functions that depend on time minus t e to the minus t. Okay, so now my general solution will be C1 x1 plus C2 x2. And hence x will be C1 e to the minus t plus C2 t e to the minus t. I need to evaluate now this expression at t equals 0. So x at equals 0 will be C1 plus 0 times C2 equals 1. So from here I have that C1 will be 1. So this is my general solution. And this is my constant C1. Now I'm going to need to use the first time derivative. Obviously, it is going to be C times x1 dot plus C2 x2 dot. And this is why I calculated these two functions here. So x dot will be minus C1 e to the minus t plus C2 times t times all this expression here. Sorry. This expression here, C2 times e to the minus t minus t e to the minus t. I need to evaluate this again at 0. So minus C1 plus C2. This whole thing will be 1 because this quantity here will become 0. And this is 1. Okay, so this will be C2 times 1 equals 0, which of course means that C1 will be equals to C2, which of course means that C2 will also be 1. And hence I found my second my second constant C2. This means that x is going to be, just come here and place C1 and C2 1. So it is going to be e to the minus t plus t e to the minus t. And because later I'm going to need to jump to state space model, let me also calculate the first time derivative, which is going to be minus e to the minus t plus e to the minus t minus t e to the minus t. And of course, these two will be cancelled. Let me just put this square so that I will be able to identify it easily. And hence, x dot will be minus t e to the minus t. So this is effectively the solution of the first bit regarding, let me just zoom out. Okay. You can have all the solution here, excellent. So now this is how I have answered effectively the first part of this exam question. So let's go now to page 2. Now I need to go from the ODE to the state space. So let me rewrite my ODE minus 2x dot minus x. So the first step is to isolate the highest time derivative, create as many state variables as the order of the ODE. The first one will be x, the second one will be x dot. Take the first time derivative, x1 dot equals x dot, but x dot is x2. X2 dot is x2 dots. So this is x dot. X2 dots equals from here minus 2x dot minus x. And hence now x dot is minus 2x2, x is minus x1, so x2 dot. So now these are my two ODEs. And now all of that I have to do is to put them into a matrix form. x1 dot, x2 dot equals x1 and x2. Obviously, this is going to be 1 here and 0, because I can write this as plus 0 times x1. And once again, I have said this so many times, the typical mistakes students put here -2 and -1, because we have this sequence here, but obviously the coefficient of x1 is -1, and this is -2. So now this is my state space model. Because I will need to solve this state space model, I need to find the initial condition. Okay, so if this is x dot, obviously this is going to be x. So the vector x at 0 will be x at the instant 0, will be x1 at the instant 0, x2 at the instant 0. Okay, please remember this is a vector. And this is not this x0. Okay, just be a little bit careful about this. Okay, so x1, but x1 we know from here will be x node, and x2 will be x dot node. Okay, so the initial state vector will be 1 and 0. So let me also write it here. X naught will be 1 and 0. So when I would try to solve the state space model, at some point I will need to use the initial state vector, and it's going to be 1 and 0. Now, the next bit is to solve my state space model. I need to calculate the eigenvalues, as we know. Obviously, you are more than welcome to expand this determinant, but you don't have to do it, because we know that the eigenvalue will be 1, and this will be -1. And we know that because we found it here. Okay, it is the same system. So the eigenvalues, either as a state space model or as an ODE, they must be the same. So now this is my eigenvalue. I need to calculate the eigenvector. A minus Ri times E equals 0. This is now my A. So this expression here is minus R1 minus 1 minus 2 minus R times A1, A2 equals 0 and 0. Go and place here the value of -1, and I will have minus of -1, 1, so 1, 1, -1 here, -1 of -1, -1. A1, A2 equals 0 and 0. And this is the bit now where we can say that just adjust this again, that I'm doing the right things, because I have effectively the same equation twice. So A1 plus A2 equals 0. And then I will arbitrarily make this 1. So this must be -1. So my eigenvector E will be 1 and -1. Oops. So I have found now, well, I knew my eigenvalue, I have found my eigenvector, I have repeated eigenvalues, so I need to find the generalized eigenvector. So this is page 3. Okay, the generalized eigenvector is going to be given by this equation. So this is 1 and -1 equals, you have calculated this before, okay? Sometimes students recalculate this, but you have found this bit here, okay? So 1, 1, -1, -1 times B. Let's call this B1 and B2. Again, I have the same equation twice. So 1 equals B1 plus B2. So I'm going to arbitrarily make this 0. I can do this because this is a non-homogeneous system. And of course, this will be 1, meaning that my generalized eigenvector is 0 and 1. Okay, now let me write my two linear independent solutions. We know that x1 will be nothing more but e to the RT. And of course, x2 will be e times t plus b e to the rt. And because I'm going to need this, let me evaluate this at the instant 0, which is going to be just e. And of course, x2 at the instant 0, it is going to be b. You don't have to do it now, but it is going to help me with my equations later. So now my general solution is c1 x1 plus c2 x2. I'm going to evaluate this at the instant 0. So c1 x1 at the instant 0 plus c2 x2 at the instant 0. So I can just put them now, c1 times e plus c2 times b equals the given or the calculated now initial state vector 1 and 0. But what is e? E is 1 and minus 1. So c1, 1 and minus 1 plus c2, c2 times b, b is 0 and 1 equals 1 and 0. So I have c1 times 1 plus c2 times 0 equals 1. So I can immediately say that c1 will be 1 minus c1 plus c2 equals 0. Hence, c2 will also be 1. It's really important that you learn how to do this rather quickly and try to avoid making mistakes. So now let me try to find my specific solution. So this is page 4. So x will be obviously c1 x1 plus c2 x2. I have just found that these two constants are 1 in both cases. So I will make this x1 plus x2. So e times e to the minus t plus e times t plus b e to the minus t. Let me isolate the e to the minus t in both cases. So e to the negative t times e plus et plus b e to the minus t. Okay, let me do one more step. E plus b plus e times t, just to isolate, to group better together the constant terms. E to the minus t, and now I have here 1 and minus 1 plus 0 and 1 plus 1 and minus 1 times t. Okay, let me isolate the specific, let me indicate better the specific components. This is e, and this is b. So now this is going to be e to the minus t. I will have 1 plus 0, 1 times t plus t. And the second component is going to be minus 1 plus 1, so 0 plus minus 1 times t minus t. And this is now my solution. And if you cross-check this with what I have previously found, it is identical. So it is 1 plus t and minus t. So indeed, I got to the same solution. Okay. Tidy up my papers here. And now we are asked to solve this once again using now the state transition matrix. Let me just remind myself, R is 1 minus 1. My eigenvector is 1 and minus 1. And the generalized eigenvector is 0 and 1. Okay, and also, of course, x1 will be e times e to the minus t, and x2 will be e times t plus b e to the minus t. And now the fundamental solution matrix, obviously it is going to be x1 and x2. And of course, this is going to be now from here e times e to the minus t. And from here, I will have e times t plus b e to the minus t. Let me once again take out the e to the minus t because it is going to help me later. So the fundamental solution matrix is going to be e to the minus t times e, et plus b. Okay, let me go to page 5. Let's be sure that I'm recording this and I'm not just talking to myself. Okay, it is recording. Okay, so I have just found that the fundamental solution matrix is going to be e to the minus t, et plus b. So this is my fundamental solution matrix. Anymore. Okay, then obviously the fundamental solution matrix evaluated at t equals 0. It is going to be E and B, as we expected that. It is going to be hence 1 and minus 1, 0 and 1. I need to find the inverse. So first of all, I need to find the determinant. It is going to be 1 times 1 minus 0. So it is going to be 1. So it's a very nice matrix. So the inverse of the fundamental solution matrix at t equals 0, I'm going to swap these two places, so nothing will change here. And I'm going to change the signs of these two, so 1 and 0. And hence now my solution is going to be the fundamental solution matrix at t equals t times the inverse of the fundamental solution matrix evaluated at t equals 0 times the initial state vector. Let me isolate first of all these two. We have seen this trick in the class. This will be 1, 1, 0, 1 times 1 and 0, which is my initial state vector. Okay, and of course, I will have 1 plus 0, 1 plus 0, so 1 and 1. And now my solution will be this, which is going to be this, so e to the minus t times, let me write it directly, minus 1 and 1, and the second will be minus 1 and 1 times t plus b, which is 0 and 1 times 1 and 1. Before I do the multiplication here, please allow me to a little bit do the maths here. So e to the minus t, it will be minus 1 and 1. This is going to be minus t plus 0. And then this will be t. This will be t plus 1. Oh, I have done a mistake. Sorry. E is not minus 1 and 1. It is plus 1 and minus 1, plus 1 and minus 1. So E is 1 and minus 1. Sorry about this. So this is going to be now e to the minus t, and I was thinking that this doesn't work. 1 and minus 1. So this will be t plus 0 and minus t plus 1 times the initial state vector, 1 and 1. So this will be e to the minus t. We will have 1 plus t. I'm going to have here minus 1 minus t plus 1. So the solution is going to be 1 plus t e to the negative t, and now this one just minus t. Which of course it is exactly the same of what we have calculated previously. So indeed, with all three methods, I'm getting the same result, and this is what you should answer at the last bit. Okay, so with this one, I have finished the first question. Let's go now to see the second question. So we have covered all of these bits here. Now, let me go to question 2. In order for me to answer this is page 6. So let's see that. We have a state feedback controller that will give you this closed loop state matrix. When will this happen? Under no estimator and with an estimator. Okay, so let's see the answer to that. Okay, so effectively, this is going to be question 2A. ACL will be A minus BK. We know that this will happen when U is minus KX. And when U is going to be minus KX, if you have no estimator, If you have no estimator, the only way that this can happen is when the output matrix will be the identity matrix, because in that case, y equals c times x, we know that this is the output equation. If c is the identity matrix, y equals x. So instead of having the typical state feedback, we can have an output feedback, which is going to be exactly the same. And of course, when with estimator, this will happen when the error converges at 0. So you are feeding back the estimated state vector. Sorry. The error will converge. Okay, the error will converge at 0. So the estimated state vector will converge to the real state vector. Now, let me just go to see the next question, B. The next question, B, this is capital A, this is capital B. It is directly taken from your handouts. So I'm not going to spend my time on that. And now this is something that I would like to better explain, because if you just read this exam question, it's not going to be clear to you how to answer it. This is because A, back in 2018, I was not doing the integral action. So they had only one controller for a non-zero steady state, and that was the tracking controller. And also the derivation for the constant of K1 was much harder. It was much harder because the output equation in your handouts it is y equals c times x. Back in 2018, oops, sorry, you cannot see what I'm writing. So in your handouts, the output equation is y times equals c times x. In 2018, I was also adding the d term, and if you add the d term, the whole analysis is very difficult. So if I would like to map that exam question to this year's material, I'm going to do it like this. Oops. I need to determine all the steps so that I can have tracking. I can have state, feedback, and also I can have an estimate. Okay, now for the tracking, you need to prove. So I'm going to give you K1 equals minus C, A minus B, K minus 1 times B times minus 1. So this is given. And you have to prove it. We have seen this during the revision class. Then going for the state feedback, we all know that there are only two steps here. The first step is to check the controllability. So what you actually write here is, my first step is I'm going to prove that the system is controllable, and then choose your closed loop eigenvalues. Let's call them R1 and R2. And then for the estimator, we need to check that the system is observable, and that of course we need to choose the closed loop error dynamics at 10 times R1 and 10 times R2. Okay, meaning that the estimator must be a lot faster. And this exam question, it's also asking the block diagram. The block diagram is directly from your handouts. So I will not spend time now going through the handouts. So that was question 2, ABC. I would say a rather quick question, bonus question, without any calculations, which can help the students that they have properly understood this material. Okay, now I go to question 3, which is the last question for this paper. And the first one, okay, let me show you question 3. It is asking to check the controllability of all these systems, but it is without the controllability and observability matrices. Please read the exam question very carefully, because the students that they used the controllability and the observability metrics, they got 0 marks from here. Okay. Now, in order for you to answer this exam question, all that you have to do is to write down the ODEs and the output equation. So for the first system, I have x1 dot equals x1 plus u, x2 dot equals 2 times x2, and the output equation is x1. Obviously, now u can influence x1, but as you can see, u cannot influence x2, so this is not controllable. It's not controllable. Also, I can see that y can see only x1, so I have no idea what happens at x2, so the system is not observable. The second system is a very similar one. The ODEs are the same. But now the output equation is only x2 for exactly the same reason as before. The system is not controllable, not observable. Okay, now I can measure x2, but I have no idea what happens at x1. Going now to the third system, I have the same ODE. So I can immediately say that this system is not controllable. Obviously, in your answer, you're not just going to cross this, you're going to write, you cannot influence x2, so the system is not controllable. Now, the output equation is x1 plus x2. I can see that my output will have information both for x1 and x2, so this system is observable. Going now to the fourth system, we have x1 dot equals x1 plus x2 plus u, but the second ODE remains the same. So I can see that the system again will not be controllable. The output equation is though again y equals x2, so in exactly the same way as here. So this system is not observable. Then we go to the fifth and last system. I think it is the last one. Yep. x1 dot equals x1 plus u, so exactly the same as previously. But now x2 dot will be x1 plus 2 times x2. Okay, so effectively u will influence directly x1 and indirectly x2. So this is our controllable system, CTRB. And the output equations now is y equals x1, y2 equals x2, y3 equals x1 plus 2 times x2. And that system is also observable, because I have x1, I have x2, and I have their linear combination. So I have all the necessary information for both states. So this is how you were supposed to answer this exam question. Once again, I like it because you don't have to do calculations, and you can easily demonstrate your understanding. That was question A. Go on to question B. Let's see that. Yep, that was A. Now I have to go to B. Page 8 for me. We need to comment on the following systems. Okay. Obviously, the eigenvalues in the second case are 100 times deeper into the minus infinity area. So what I'm going to write here is the system 2 is faster. Oops, this is B, is faster as eggs deeper into minus infinity area. Okay, so you have pushed the eigenvalues 100 times deeper into the minus infinity area, so it is 10 times faster. Let's see the next bit. The next bit is asking me to classify these systems in terms of oscillations, if you have any. I think it's clear that the third system, one and two, I will keep writing on my visualizer and then you will see what I have written. So it is clear that the third system has no oscillations because there is no imaginary part. We know that the frequency of the oscillations will only depend on the imaginary part. Then we go to these two systems. So to this one, I can see that the imaginary part is plus minus 1. The imaginary part here is plus minus 100. So let me call this system 1 will have some oscillations. System 2 now, let's say more oscillations. And now we come to this bit, system 4. And some of your fellow students wrote that this system will be between 1 and 2. But this is completely wrong because I have the same eigenvalue twice here. And we know that if you have a real system and you have a complex eigenvalue, you must always have the complex conjugate. So for this bit, the answer is so no oscillations, some more, not a real system. Okay, you must always think about these things. So let's go now to the next bit and determine the stability. So 1, 2, 3. Okay, then in order for me to check the stability of a system, I need to check the real part of my eigenvalues. I can immediately see that this is going to be unstable because I have a +2. So cis3 it is unstable. Unstable as there is one eigenvalue is at plus or just positive. The same thing is with cis2. It is unstable, but now the real part is positive. You can see that the real part here is positive. And of course, cis1, it is stable because the real part is negative. Show you. Let me also write it like this. Positive and negative. And now we go to question C, which is a nice question. Effectively says, again, I would say this is a bonus question. It is giving me a third order system with the eigenvalues at -1, -2, and -3. So the solution will be, we have seen this in the class, C1 e to the -t plus C2 e to the -2t plus C3 e to the -3t. This is my general solution. And now I go to the last question of this exam paper, which is D. And I really like this exam question because once again, it is testing our understanding. It's pushing us a little bit further. We have the eigenvalues of -1, -2 as before, but the last one is a rather large number. Small if you want to put the minus sign in front of it. So as before, my solution is going to be C1 into the -t plus C2 into the -2t plus C3 into the minus whatever, how many zeros I have here, t. And then you are being told to approximate this by using only two terms. So I want to approximate this. Okay, so this is the symbol to approximate. Now, if you see these three terms, say at t equals 0.1, this will be non-zero, this will be non-zero, but practically this term will be zero, meaning that this term will be extremely faster than these two. So effectively, this will become zero very quickly. So the approximation here is going to be C1 into the -t plus C2 to the minus 2t. And this is my solution. And this is how I have solved the exam paper from 2018-2019. I'm going to stop the recording now. I'm going to upload the recording onto Canvas, and I'm going to scan, as always, these pages, and I'm going to then email you to inform you about all of these things. As always, if you have any questions, just let me know. Thanks. Take care.